I just want to introduce Muriel Niederle. She's a professor of economics at Stanford University, and she's going to talk about gender differences in competitiveness. So.
I guess I'm going to be the lone economist in this conference, given that Andy Kaplan was delayed by the storm. So I'm happy to defend the whole economics profession, but I wouldn't mind if I don't have to, immediately at least. So I'm going to talk about something which is actually not very common for economists. I'm going to talk about gender competitiveness and career choices. And introduction is going to be a very standard economic introduction, and maybe we'll show you why economists sometimes look at questions very differently. We are often interested in very big questions. We really care about answering those questions. I guess so are you. But so here's my big question. It's going to be, we have all these gender differences in economic success. There are very few women who are CEOs compared to men. There's this glass ceiling effect. It's a gender wage gap. And more specifically, there's also quite some gender difference in education. When you look at the US, it is actually now the case that girls are as likely as boys to take advanced math classes, but this is not used to be the case. When you look, however, at very high levels, you still see a big gender gap. There's a recent nice evidence that this is not driven just by ability. The way to show this is that very high boys who go to this American Math Olympiad equivalent come from basically all over the US, whereas the girls come from a very small set of schools. So that suggests that maybe for boys, we look at ability, and you would imagine that it's somewhat randomly distributed over the US, whereas for girls, there seems to be other factors that are in place that prevent some of the girls who are not in one of these select set of schools to actually make it to the very top. In Europe, we have a big gender difference in how much math and sciences girls take compared to boys. And even in the US, on the college level, there is big gender gaps. Okay? Why do we care about STEM, or science, technology, engineering, and math? Well, one reason we do is that they're actually highly predictive of how much money you're going to make in the future. Okay, so the goal is going to be to try to understand this. And standard economic answers have been discrimination or gender differences in abilities or preferences. And the goal here is going to be to find a different reason or different attribute, which is going to be a psychological attribute. So maybe that's why I'm here at this conference. And we're going to find such an attribute that is large and robust and can help us understand these differences. And this is a big chunk of my career. So the attribute we're going to think about is competitiveness. Okay, so the goal for this talk is going to be to show you that we have gender differences in competitiveness. We're going to find these first in the lab, where we can very precisely study them. We're going to see whether these are robust and really there. And then the next step is going to be to show this external relevance for this finding that we have in a lab to the field. To really, is it going to help us understand these gender differences in education and labor market outcomes? And at the very end, this is the third point. It takes a lot of space here, but unfortunately, that's hopefully only in the next 10 years or so. We want to think about where do we go next? I mean, one thing is we can think about changing the competitiveness of people. We can think about changing institutions so that some of these traits don't matter that much. But I will only spend a little bit of time on that at the very end. Okay, so as an economist, I actually took a lot of psychology classes. And when I got interested in this question of competitiveness, I looked at a lot of psychology literature. And the literature would often say that boys spend more times at competitive games than girls, who often play like house, which is a game without any endpoint. Men describe themselves as being more competitive. And as economists, for us, this is a little bit frustrating, because the question is, well, suppose we level the playing field, we make high stakes. Are we still going to observe these differences? So in order to do that, we need really clean data. So what we're going to do is we're going to go to the lab. The advantage is in the lab, we can control self-selection issues. We can measure performance, right? If it's a difference in performance, if boys are faster runners, obviously, girls are not going to run against the boys because it's going to be boring. We also don't have to worry about discrimination because, at least in economics, we never lie to subjects. So if I say you're going to be paid as a function of your performance, you're going to be paid as a function of your performance. We also don't have to worry about career concerns, right? Here's another reason why girls are not, or women are not CEOs, is that maybe they want to spend more time with their children. Our lab experiments are going to be 1-hour lab experiments. If you want to have children later on, that's just fine. In economics, we have a different. So I put my co-authors in the beginning instead of at the end. I just noticed that we have a bit of a different, I guess, way of dealing with this. So here are a bunch of papers that I have written on the subject, and I have a lot of co-authors who I want to thank here. And I'm going to show you a subset of those papers. So the first, which is actually my second study on this issue, but it's going to be the one that really helped me bring this to the field, is a joint paper with Lisa Wesselund, where we try to establish these gender differences in competitiveness. Okay, so let me show you how we do that, and then think about the external relevance for that finding. So this is an experiment that we ran at Pittsburgh University with students from Pittsburgh and Carnegie Mellon. We had 80 college students in total. In an experiment, there would always be groups of 2 men and 2 women who perform a real task multiple times under different incentive schemes. The performance of others is not going to be known until the end of the experiment. So if I sit in the experiment, I'm just going to perform this task and not going to hear anything until the very end. And we never, ever mention gender. Okay, so when they come to the room, we seat them so that in every row there's going to be 2 men and 2 women, but we never mention the word man or woman or male or female or gender, because we did not want him to think that this is about gender. Our goal is to see whether women shy away from competition or whether men compete too much. So the goal eventually is going to be, we're going to ask them, do you want to be in a tournament, in a competitive environment, or do you not want to be? So in order to do that, we need a task where men and women are kind of going to be equally good, more or less. Here's the task we picked, adding up 5 2-digit numbers for 5 minutes. Okay? So you're going to do this many, many times, and we're going to count how many you do correctly. So I thought, this is a very easy math task. This is not even math. I'm a mathematician by training. So this is, for me, this is just being careful. But some people objected afterwards to me that this is a math task, and there are all these gender differences in math. But when you look at literature in psychology, it's a bit of a better lens, and you see that these gender differences in math only apply for very difficult or higher math, not for at these very early stages. So our benchmark performances, so you come to the lab, first we're going to say you have 5 minutes, solve as many of these problems as you can. If we pick round 1 for payment, then you're going to get 50 cents for every correctly solved problem. Go ahead, solve your problems. You solve these problems, you have no idea how many problems other people solved, but you're going to learn how many of your problems were correct. Okay? Once you're done with this task, you're going to say, okay, now, you remember you're going to do it 3 times, so here's the second time when you're going to do it. We're going to put you in groups, and your group is going to be your row, and your row is going to happen to be 2 men and 2 women. What we're going to say now is that if we choose round 2 for payment, we're only going to pay 1 person. It's the person who solves the most problems correctly. And that person is going to get $2 per correct problem, and everybody else is going to get nothing. Okay? So 5 minutes, solve problems. At the end of those 5 minutes, again, I just know how many problems I solved correctly. I have no idea whether I won the tournament, nor do I know how many problems the other people in my group solved correctly. Okay? So what do we find? Here are the average performances in the piece rate and in the tournament. So boys and girls, or men and women, are more or less the same. In the piece rate, women solve about 10.2 problems, men solve 10.7 problems. The difference is not significant. In the tournament, it's 11.8 and 12.1. Again, the difference is not significant. This increase, by the way, is mostly due because they do it a second time. They learn not to use pencil and paper. That just slows them down. Obviously, they don't have calculators. And there on the table below, I show you for each number of correctly solved problems, what's your chance of actually winning the tournament. Okay? And what you can see is that if your performance is 13, you have about a 25% chance to win the tournament. So you're just indifferent between the piece rate or the tournament, because in the piece rate, you get 50 cents for sure. In the tournament, you get $2 if you win. If you have a performance of 16, you have an 80% chance to win the tournament. Okay? What that means is you have an 80% chance to win $32. If you would choose piece rate with a performance of 16, you're going to get $8 for sure. Okay, so this is a huge difference in earnings. So now comes the third task, where we ask them to choose between two different incentive schemes. Right? They just did a piece rate, they just did a tournament. Now we say you're going to perform once again, but you decide how to get paid. If you choose piece rate, you're going to get 50 cents per correct problem. If you choose tournament, what's going to happen is I'm going to take your new performance, I'm going to compare it to the past tournament performance of everybody else in your group. Okay, so I'm from Austria, we do a lot of skiing. Think about, we all ski downhill, and now I get asked, I can ski once again, and my new time is going to be compared to everybody's old time. Okay? If I choose tournament, I'm only going to get $2 if my new performance is better than the other guy's old performance from last time in the round 2 tournament. Otherwise, I'm going to get $0. Okay? The advantage of doing it this way is that I do not impose any externality, as we say in economics, or my choice does not have any impact on, say, Schacher's choice or Schacher's payment in this round. Right? Because I choose tournament, I'm going to compare my new performance to his old performance. So he doesn't care about what choice I make, and I don't care about the choice he makes. So we turn this into an individual decision-making task, which means I don't have to worry about what they think about what other kids or other people are doing, other college students are doing in this example. Okay? So what would we expect? Right? So let's assume that the new performance is going to be exactly the same as the one in round 2, because by the second time they do it, they actually go out faster, and then it turns out learning stops. So if the performance would be exactly the same as before, remember, if you have a performance of 13, you're indifferent. If you have a performance of 14, you really, really make more money with the tournament. We would expect about 30% of women and 30% of men to enter. If you add the ones who are kind of indifferent, who do 13, we have 40% of women and 45% of men. So what do we find? This is what we find. Okay? 35% of women, 73% of men. Okay?
Clarification.
Yeah.
At this point, do they know what the thing is they have to eat and what their performance is?
No. So remember, you just know what you heard at the end of the second round tournament is how many you did correctly. That's it. You have no idea if you won. You have no idea how much more you did than I did. You actually have no clue how much I did. Mm-hmm. Yeah, you have 5 minutes. You know how many you did correctly. Yeah? Mm-hmm. So we tell you, how many were wrong. Because it's on a computer, it's actually easy to do. Once you're going to do some paper and pencil, it's going to be a bit harder to do that. Okay? So how does the performance predict entry? So what I'm going to show you here on this figure is I'm going to have on the 4, it's going to be the bottom 25% participants in terms of their performance. And we're going to show you for the men in that group and for the women in that group, how many of them entered the tournament. Okay? And 1, these are our 25% best participants. And I show you how many of those, what fraction of men and what fraction of women in that group entered the tournament. The men always enter the higher fraction of the women, even the men who have no chance of winning. Once you're in group 3 or 4, you have no chance of winning. We have about more than 50% of men entering. Okay? We never have more than 40% of women entering the tournament. So who's going to lose money? It's going to be the high-performing women. They're going to lose a lot of money. And the low-performing men. Now, they're not going to lose that much money, because if you don't do that much, you're not going to make that much money anyway. Okay? But it's both groups that make mistakes. Okay? So, I guess your question maybe lean to this question is, well, what's going to matter is I know my performance, but what's going to matter is how good I think I was compared to other people. Right? So maybe a lot of this gender difference in entering the tournament, what we want to call competitiveness, is actually just driven by gender difference in beliefs or confidence. Okay, so what we do is, before they get any feedback, we ask them, how good do you think you were in the round 2 tournament? When we all did the tournament, I'm ask you, okay, do you think you were first, second, third, or fourth in your group? If your answer is correct, I'm going to give you $1, otherwise you get nothing. Okay, so that we think helps me at least incentivize you to give an answer that is as correct as possible. So the 2 questions we can ask. One is, are men and women are going to have different beliefs about how well they did? And second, are those beliefs going to determine this difference that I just showed you? So first, let me show you what they say about their rank in the round 2 tournament. 30 of our 40 men thought they were the best in their group. Okay? 17, I mean, the women were also a little bit overconfident, okay? 17 of our 40 women thought they were the best in the group. Now, of course, most of the men are wrong, because not that many can be at the very top. So we do find that everybody's a little bit overconfident, but men are vastly more overconfident than women. The other thing you note is that we have about 75% of men who think they're the best in the group, about 40% of women who think they're the best in the group. Right? So in principle, that would line up perfectly with the fraction of men and women that entered the tournament. Okay? So what I'm going to show you now is for each belief, did I enter the tournament or not? Okay? And what you see is that among the people who thought they were the best in the group, we have 80% of men entering the tournament, but only 50% of women. Even among the people who thought they were second, we still have this gender gap in tournament entry. Okay? And there are actually very few people who think they're fourth. So this point doesn't have a lot of data points. Okay? So what we find is that even conditional on beliefs, men are going to enter the tournament more than women. And we have additional treatments to show that this gender difference in tournament entry is not driven by gender differences in risk aversion or gender differences in aversion of knowing whether I was the best or not in my group. Okay? So, our conclusion in this paper was that women do not decide to enter the tournament because of these psychic costs of performing in tournament, or this would be called as gender differences in competitiveness. Some of it is explained by confidence. About a third of this gender gap can be accounted for by gender difference in confidence. But risk aversion or not wanting to get feedback about your relative performance did not play a big role. Okay? So the nice thing in economics is that other people can replicate your experiments and still publish those nicely. So this was something that lots of other people looked at. So nicely for me, there were many people who followed up on this. And last year, we published a review paper that this finding seems to be very robust. So there are many other teams who do not even remotely involve me or my co-author who find this gender gap in competitiveness. Sometimes the gender gap is attenuated, especially in stereotypical female tasks, but not always, like word tasks. Sometimes it's also attenuated when people receive feedback. But overall, there was very little evidence that risk aversion plays a big role, even though, and in general, when you control for beliefs or performance and risk attitudes, you still get this big gender difference in tournament entry decisions. Okay? So that seems to be very robust. So what is the question? No. So the question is this competitiveness, is that going to be important? Let me just see how much time did I just spend? When did I start? Did anybody? Okay. Perfect. Okay. So the question is going to be, is this competitiveness, is that really going to be important? Okay, so we find this in the lab. It is very robust. And it was very good for us to start in the lab, because in the lab, if I would have done the same thing in a workplace, you might have worried about child rearing, you might have worried about, can I really measure performance that well? Maybe there are other aspects that play a role. You may have worried about, maybe if I'm a woman, I worry that my supervisor, is not going to promote me, so there's no reason for me to even work hard and try to enter this competition. So in the lab, we could get rid of all of these problems. We find this big effect. And I guess for those of you who have done gender differences, this is a big effect. I mean, we don't need a lot of heavy econometrics to show that these differences are significant. Okay. So, but now the question is, my colleagues, they say, this is nice, we do all this lab stuff. I have a lot of fun with it. But the question is this really going to help me explain gender differences in education or gender differences in labor market outcomes? Okay, so this is going to be, for us now, the next task to show that everybody kind of should care about this gender difference in competitiveness, even if you want to go outside of the lab. Okay, so one way to think of that is, some psychology uses the term external validity. In economics, this term unfortunately got a little bit muddled. Often in economics, people are happy enough to show external validity in the sense that Austrian farmers are going to have the same problem. But this is not what we care about. We care about average women in economy. Is that going to impact whether they're going to study math or not. Okay? So that's what we're going to show. Can this gender difference in competitiveness help us account for these gender differences in, and what we're going to focus on, decision of studying science, technology, engineering, and math. And the way we're going to do that is we're going to try to correlate a lab measure of competitiveness with the choice they make outside of the lab. So a little bit like what we have seen this morning. Okay? While Schacher was very happy to say that this is what we all should be doing, this is actually, also for economists, actually very rare to do. And this is something that is very new and we just started doing. And often, it is actually not that easy to find this correlation. As, again, I'm sure many people who have done stuff know that this is not so obvious. So in order to do that, I have two co-authors from the Netherlands, Thomas Boozer and Hessel Oosterbeek. And the advantage of the Netherlands is that, like in many places in Europe, when you go to school, you don't have a lot of choices. You all do the same thing. So here we're going to focus on the 20% of kids who are on this pre-university track. So these are the top of the crop of Dutch students. And after 3 years of middle school of this pre-university track, they have one choice to make for the last 3 years of their high school. That's between choosing one of these 4 profiles. The first profile is nature and technology, called NT, nature and health, economics and society, or society and culture. The above is the order of how much math you're going to have for science. It's also the order of prestigiousness. So when you ask an average Dutch person, what's the most prestigious track and so on, then he's going to give you the same order. What happens is that girls are less likely to choose the most prestigious track, the NT track, and they are much more likely to choose the least prestigious track, the literature track. So we want to try to understand this choice. So we're going to ask, controlling for academic performance, so if I would know their grades and everything, does this competitiveness variable that I'm going to try to measure like I do in the lab, is that going to predict choices? And second, is that going to help us understand some of the gender gap in choices? Okay. So in order to do that, we approached schools in and around Amsterdam, and 4 schools allowed us to get at every single one of their 9th graders. That's in a few months before they have to make that choice at the end of 9th grade for the last 3 years of the high school. We have on total about 400 children. We have to kick out a few of our sample because some of the kids come late, so then they don't do the experiment. For some kids, we didn't get the school data because they have to repeat the class. So in the end, we have a sample of 362 children. We ran the experiment in March, April, and May. The children have to make the profile choice at the end of June. So school ends at the end of June. And then in the summer, we get the data from the school about the grades of those kids and the choices they actually made. Okay. Within a school, we ran the experiment on the same day, mostly exactly the same time. So we're not worried that they kind of talk to each other. Across schools, and the school in Amsterdam is not that small, so across schools we may have had different weeks where we ran the experiment, a different month. So we're going to do this gender competition task that I just showed you. We're going to adapt it a little bit to 15-year-olds and to the fact that we only have a 1-hour class, which is 45 minutes. So instead of adding up 5 two-digit numbers for 5 minutes, they're going to add up 4 two-digit numbers for 3 minutes. We're going to have to do paper and pencil because they don't have all laptops. They're going to do 3 rounds of performance, and they're not going to get any feedback, just like in the experiment before. We're going to pay one of the rounds. We're going to select that at the end of the class hour, and then we pay them a week later. Okay, so any information they're going to get only a week later when we collected all the results and actually computed how many did correctly and who was the winner of the tournament. So they're going to do the round 1 piece rate, where if we use this round for payment, they get €0.25 per correct problem. Then we do the round 2 tournament, where the winner would receive €1. In the way we did the tournament, we said that you're going to compete against 3 other kids in your class. We don't tell you yet who, because we're going to take the results, go home, and then we're going to randomly assign kids to groups of 4. Okay, so we can't tell you who the other 3 kids are going to be, because we actually don't know yet either. At the end of the round 2 tournament, we just collect your paper and pencil filled out, adding up numbers. You're not going to hear either if you won the tournament or how many you did correctly, because, again, we don't know yet either. And then you're going to do this choice, right? You have a choice between, for the third round, if you pay it, either the piece rate or the tournament. Okay. We also ask them this confidence question. So at the very end, we ask, remember the round 2 tournament? How good do you think you were in your group? 1, 2, 3, or 4? And then we ask them some risk questions. The risk question is going to be 1 of 5 options. You either get €2 for sure, or you can have a 50-50 gamble between €3 or €1.50, €4 or €1, €5 or half a euro, or €6 or nothing. We also ask kind of a verbal risk question. How do you see yourself? Are you generally a person who is fully prepared to take risks? And that's just a non-incentivized question. Where from 0, I'm unwilling to take risks, to 10, where I'm fully prepared to take risks. We also asked them about how they feel about their math ability. The reason we did that is we're going to get from the school the math grade, but you might worry that the math grade is actually not the best predictor of the math ability. Maybe it just says, I'm also a very careful person, I don't make mistakes. So we wanted to ask them how they think about their math ability. Now that, of course, might already tap into the confidence question. Okay, so if anything, we might make it a bit harder for us if we control for this as well. But that's fine, making it harder for us is okay. So we asked them, what do you think is your rank in math in your year, between the best 25% to the worst 25%. We also asked them, how difficult is it for you to pass a math class? From 0 to very easy to 10, very hard. We also asked them, what profile do you think you're going to pick in June? And then we asked them, what profile do the best students pick? And then, as I said, in the summer, we get from the school the profile they actually picked, and we get the grades for all the students. Okay, so the reason the Netherlands, or probably any European country that has this choice is ideal is that before they make this choice, they all have the same experience. They go to class together, from morning to evening. They don't have different teachers. There's no other choices they can make. Okay, so it's not like in the US where you select. It's not like at the university where you just choose, what class you want to do. And then they have this one choice to make. Okay, so they all have the same environment, and then they have one choice to make. Here are the different tracks. So this is just to convince you that indeed one has much more math and science than the other. The B is the hardest math. Actually, D is the hardest, then B, A, C. What you do in those tracks depends, that's going to determine what you're going to do in college. Mostly because some of the better universities at least, they're not going to accept you if you didn't do the right track. So if you want to become an engineer or mathematician, you have to have taken a math track. Most of the people who take the math track become, go to science and engineering, whereas people who take the literature track, say, go to humanities, social sciences, a little bit lower. The other thing you notice is that people in the NT track and the math track are also more likely to actually go to university. So that's already going to be a sign that this order of prestigiousness is probably somewhat correct, in the sense that the NT track is probably going to attract the best students. Okay, but let's check about this prestigiousness of profiles in our sample. So I'm going to show you the average academic performance of the kids that choose the math track and the health track and the economics track and the literature track. And I'm also going to show you what kids answer to the question of what they think where the best children go. Okay, so here you can see, so the GPA goes from 1 to 10, but 10 is the best. And you can see that the children who go to the NT track, the math track, have a higher GPA than those who go to the CS track, for example. You also get the same ordering on the math grades. You get the same ordering on how good I think I am in math compared to other people in my class. There's the math quartile, math difficulty. People who go to the NT track think math is easier, so 0 was very easy. And relative math is your relative rank in your class, yes.
When you ask them what are the best students,
Mm-hmm.
do you differentiate gender at all?
No, we just asked them, where does the best student go? But I can look at this by gender. And what you can see is that the boys and girls, they kind of more or less agree on their ranking. Not perfectly, but quite a lot so. For the thing I'm going to show you for now, I'm going to take that order as given. But in the paper, if you want to check, at some point we use the student-specific ordering. Okay, so if you have a different order, I can still ask the question, well, did you take what you think is the most prestigious one? Okay, but here, for this talk, I'm just going to take this order as given that so many people agreed on that order. Here is the profile choice by gender in the Netherlands. Okay, not just in our sample. This is not our sample yet. So what you can see is that boys are 3 times as likely to choose the NT track, and girls are 3 times as likely to choose, 4 times as likely to choose the CS track. Okay, yes.
Are students guaranteed a spot in the track they select?
Yes. So the way that works is that it's really your choice where you go. Now, if you're really, really bad in math, or if you're really, really bad in Latin, we're going to tell you maybe you should repeat the class before you make that choice. Okay, but there's no restriction. So I went through the French high school system, which has exactly the same choices. Okay, so the fact that girls are so much more likely to go to this literature track, which is, it's a little bit of a, for better or for worse, trap. Okay. They wanted to abandon this track, okay, because they said this is just, we have these 15-year-old children, they make this choice, and then they are kind of stuck with it. So that prompted a huge debate, but in the end, this is actually not, in the Netherlands, they started these tracks only somewhat recently, so they decided to stick with it for now. Okay. Here is what the kids in our sample look like. We have about 40% of boys going to the math track compared to 70% of girls. And we have 15% of girls going to the literature track compared to 8% of boys. Okay, so we have kind of the same pattern, a little bit less extreme. This could be either because of time, but these kids are going to finish only 3 years, whereas the data from kids who finished 2 years ago. It could also be that schools in Amsterdam are a little bit different, that maybe in the countryside the differences might be bigger. Okay. The other thing to see is that when you look at grades or the GPA, if anything, girls are better than boys. In math, there's no difference. In the GPA, girls are better. However, when you look at how good I feel about my math ability, girls feel that they are less good in math than boys are. Okay. So we find what we expected to find, that girls are more likely to choose the math track than boys. Boys are more likely to choose the math track, and girls are more likely to choose the literature track. In the rest of the talk, I'm going to show you, I would be happy to just show you pictures, but unfortunately this doesn't work with this data, so I'm going to have to show you some regressions. But to make it easy, I'm going to focus on the important variables. So we're going to run ordered probability regressions to predict the choice people make by the order of prestigiousness. And the variable to focus on that is going to be helping you understand what's happening is this variable, female divided by cut 3 minus cut 1. So the way to think of that is when you look at the first regression, this tells you that girls bridging the gap between choosing the least prestigious to the most prestigious profile. Okay, think of that gap as having a length of 1. Being female bridges 20% of that gap. Okay, so being female in itself is going to bridge 20% of the gap between choosing the least prestigious profile and the most prestigious profile. Once I also control for grades, that actually jumps up, now bridges 22% of the gap. And that's not surprising given that girls and boys have more or less the same grades, or if anything, girls are better than boys. And kids with higher grades go to more prestigious tracks. Once I add in feelings on math, this gets a little bit smaller again. Okay, but still, this female effect is quite big, right? Remember, we think about going from the worst or least prestigious to the most prestigious one. Okay, so being female on its own bridges about 15% of that difference. Another way to think of this, all our variables are normalized. So if you increase your GPA by 1 standard deviation, this is not good enough to overcome being female. Okay. So how about our experimental results? Okay, so the initial paper I told you about college children. Our 15-year-old Dutch children, are they going to be just like most of the college education that we have looked at, or most of the college kids that we have looked at in our experiments? Are we going to find that girls are indeed less likely to enter the tournament? And what is the impact of confidence and risk aversion? So here, let me just show you some statistics of boys and girls. So first, boys and girls in the round 2 tournament, which is again bold here, more or less do the same. It's no big difference. We find that 50% of boys enter the tournament compared to 23% of girls. That's a significant difference. We find that boys think that they're on average second, whereas girls think they're 2.6 on average. So the confidence, again, we have the same pattern as before, that boys are more confident in their relative performance than girls are. We see that boys are more likely to take risky options, and they're also happy to say that they are more risk takers. When we look at the difference in entering the tournament depending on performance, we find, almost like in the US data, that boys are 26 percentage points more likely to enter the tournament than girls when we control for their performance in the experiment. Okay. When we add the beliefs or the lottery, the choices over lotteries, when you look at this 26% gender gap in tournament entry, I mean, it goes down to 14%, but 14% is still quite large, even after controlling for everything we know about these children. Okay, so we have this standard result in the competitiveness that boys are much more likely to enter the tournament than girls. About a third of this is driven by gender differences in confidence. And then we have a little bit of risk aversion that plays a role. But we still have this big gap left. Okay? So the main question is, okay, controlling for academic performance, is this competitiveness variable? Is that going to be correlated with choices? And second, it's going to help me understand the gender gap in choices. Okay? So in order to show you the first question, how does it correlate with the choices people make, I'm going to show you for each of the tracks I choose. So I'm going to show you for people who go to the math track, how competitive are they compared to people who choose the economics track or the math, biology, economics, or literature track. And I'm going to show you the same for girls. Okay. So here's a figure. The average competitiveness of boys who enter the math track is much, much higher than the competitiveness of boys who enter the literature track. And for girls, girls on average are just less competitive. So they're all on average not competitive. But you get the same pattern that the ones who enter the math track are more competitive than the ones who enter the literature track. Okay. So this in itself already shows you this competitiveness variable is going to be predictive of their choices. Okay. And probably this also shows you that it probably is going to be able to account for some of these gender gap in choices. Okay. An easy way to look at this first is I can actually split my sample between boys and girls who did enter the tournament and who did not enter the tournament. Okay, suppose I focus on the first line here, boys who entered the tournament, so these are competitive boys, and girls who did not enter the tournament, these are non-competitive girls. Okay. Then how much of the gap between choosing the worst or least prestigious and the most prestigious profile is bridged by gender? Well, this is this number here, it is 36%. Okay. So if I focus on that subgroup, the very competitive boys and the non-competitive girls, being female bridges 36% of the gap between choosing the least prestigious and the most prestigious profile. If instead I focus on the opposite group, okay, I focus on boys that are not competitive and girls that are competitive, then there is no more gender gap in choices. Okay, they take the same choices. Okay. So now let me show you the same thing in more involved regressions where I control for their performance in the experiment and for their performance in the classes and their grades. So to walk you a bit slowly through this, I'm going to show you regressions of that sort where, again, we're going to have ordered product regressions. So I'm going to ask how much more likely are you to choose a more prestigious profile depending on who you are. And the important thing to focus on is going to be this female impact. So how much of the gap between choosing the worst and the best profile is bridged by being female? If I have no controls, that is 19%, more or less what we've seen before. Now I have these controls for the experimental performance in here. And this coefficient is in itself hard to interpret. That's why I gave you this one, which is easier to interpret. But you can compare the size of coefficients, okay? Because we normalize all of them apart from gender tournament entry and gender, because these are both 0-1 decisions. Okay? So when I'm going to add this entry, there are two things to look at. One is, how does this change? And I'm going to show you the difference and whether the difference change is significant. And the second thing you can check is how does the size of the coefficient on gender compare to the size of the coefficient on entry. Okay? So what you see is once I add the decision whether they enter the tournament or not, the gender gap in choices shrinks down to 15%, which is a 23% cut. And this is a significant cut. And the other thing to note is that the coefficient on entry is larger than the coefficient on gender. What that means is if I know nothing about you and I want to predict your choice, I'm better off knowing whether you enter the tournament than whether you are a man or a woman. Okay? Now let's see if this holds up when I control for their grades and how well they feel about their math ability. Okay? And the answer is yes, it does hold up. You get basically the same pattern. So if we control for their grades only, we had an initial gender gap of 23%. Once I add my competitiveness variable, it goes down to 20%, which is a drop of 12%. That is significant. And if I add on top of that how they feel about their math ability, we go from basically 16% to 13%. In all the cases, knowing whether you enter the tournament or knowing whether this person is male or female is basically equally important. And often, knowing whether they enter the tournament is actually slightly more important. So we found that this competitiveness, this non-cognitive skill, significantly correlates with choices in study profiles after controlling for grades and feeling of mathematical prowess or ability. The coefficient ranges from 75 to 130% of the size of the coefficient on gender. Controlling for competitiveness reduces the gender gap in profile choices by 18% when we account for grades and feelings of math ability. Okay? So this variable I constructed in like a 45-minute class experiment. Okay? Can tell me about as much as knowing their gender. So now you might worry that we have seen that there are these other variables that can help us account for this competitiveness, which is confidence and risk aversion. Okay, so how much of this difference is actually driven by confidence or risk aversion? How much is this residual of competitiveness? Okay? Because it's not implausible to say that maybe confidence is actually what correlates with choices and it's not competitiveness, or maybe it's risk aversion that correlates with these choices. Okay? So here I'm going to show you the same figure I showed you before, but I'm going to show you whether I enter the tournament or not, controlling not just for my performance, but also for my guest rank or my confidence and for my risk attitude. And what you see is that if anything, if you remember the old figure, this is more extreme. Okay? So it is not the fact that the reason competitiveness or this tournament entry decision was predictive is because of confidence or risk aversion. Even if I get rid of that, I get this same nice pattern. And
something with ambiguity aversion, by the way, or just risk aversion?
no, I just have risk aversion. The problem is, so these are 15-year-olds, and we have 45 minutes. Okay, so this is a big constraint is 45 minutes. It's also that sometimes the problem is how you measure some of the things, so you have to find. So anyway, this is literally all we have. I mean, if I had 2 hours, there was many more things I would have been happy to ask them. But at some point, you hit the constraints. But they were, it was actually nice that we found 4 schools that gave us literally every single one of the 9th graders. Okay, so we can do the same regressions we had before, but now instead of controlling just whether they enter the tournament, we can also control for their guest rank and for their risk question. And what you see is that here, this is always how much of the gender gap is shrinked when I add competitiveness, depending on how many other controls I have. And I guess the important thing to take home is that even if I control for everything I have, my competitiveness variable still shrinks the gender gap by 15%. So with or without controls for confidence and risk aversion, tournament entry is about and often more predictive of prestigiousness of study profile than gender. So you can see this again here. When you look at the size of this coefficient compared to the size of this coefficient, in general, tournament entry is bigger than the gender variable. Controlling for objective and subjective ability, adding this competitiveness variable reduces the gender gap by 18%. When I account also for confidence and risk attitudes, okay, instead of 18%, I have 15%. Okay, so I lose a little bit, but still have a lot left. How about just confidence? Okay, so it turns out that the confidence itself actually does not predict anything. Okay, 10 minutes. I'm actually almost done. So controlling for either objective or subjective academic ability, confidence itself is not correlated with prestigiousness of study profile choice. So one way to see this, actually, let me show you how you do this. We can look at this regression where we control for math ability and believed math ability. And then I can compare this to this one here, where I add my guessed rank. And what you see is that my gender gap in choices, if actually, instead of shrinking, increases. Okay, and the guessed rank variable is just not even close to being significant. Okay, so the confidence actually doesn't predict anything. This is not what I expected, to be honest. I didn't expect it to be humongous. I mean, I was thinking a competition would be big, but I did not expect 0. How about risk aversion? So risk aversion, we can do the same trick, right? We can look at this first regression and then the one where we just add risk aversion, which is here. So risk aversion, it turns out that going from 15.8 to 13.9 is significant, the 10% level. So it does reduce the gender gap by 12%. But somehow competitiveness and risk attitudes are kind of almost orthogonal. Not completely, because remember we go from 18 to 15% when we add these other variables. But having just risk attitudes reduces the gender gap by 12%, competitiveness by 18, and together they do it by 27%. Okay? But this risk variable is actually, even though it is marginally significant here, it actually has a somewhat big effect here. This is not the case when we look at other specifications. Okay, so for example, my own ranking, or that there's some other difficulties that I was hiding so far. So this is less robust. So I don't want it to take away that this is equally robust. Okay, it is significant in this specification, but on others it's actually much smaller and not always significant. So I think what we showed here, what we tried to show is that this competitiveness, this non-cognitive skill, or this new, at least for us economists, psychological attribute, is an important factor in educational choices. We try to bridge this gap between the lab and the field by having this lab variable and trying to predict outcomes in the field a few months later. So that helps us show the external relevance of this concept that we found in the lab. What are the open questions? Well, now that we found that this competitiveness verb is actually important, here's an obvious one. We had all these very competitive boys who choose the math track, even though they're actually not that great in math. And then we had these not so competitive girls who choose the math track. The question is, 3 years down the road, how are they going to look like? Who is going to be the one who is doing reverse? Is it going to be the not so competitive girl? Or is it going to be the hyper-competitive boy who is actually not that good in math? Okay, I have no idea. We're going to find out in a few years, hopefully, if the schools cooperate with us. The other thing is that in our environment, math intensity or science intensity and prestigiousness is perfectly correlated. I do not know how this works when this is not the case. Now, it turns out often this is the case. I have actually not seen many environments where it's not the case. But this is obviously something which I cannot disentangle with this sample here. The other question is, what exactly is this competitiveness variable measuring? Okay? So on the one hand, people tell me sometimes I'm competitive, or I feel people are competitive or not competitive, and I have a feeling I know what that means. But on the other hand, the question is, can we find other variables, maybe some variables that you psychologists have been using more often to kind of help us understand what we're actually measuring here? How much does it measure ambition? It's another thing which I have a feeling I know what it is. I have no clue how to measure it. Okay? Or big five. So there's a lot of things that we could. Now that we showed that this variable actually does something, I'm getting more interested in understanding it better. The big open question is, so we have these people who make those choices, and naively you would imagine that this is a lifetime decision in the sense that it's going to have an impact on your future career. It shouldn't depend on something like do you enter the tournament or not. It should depend on how much you like math or all these other questions. So how can we? There are two things to think about. One is, can we change the competitiveness? If this competitiveness is so important, can we make girls more competitive? Maybe by having them do sports. There are some impacts of Title IX on earnings of women. Maybe that's the driving factor. Or can we teach them to be more competitive anyway? The other question, of course, is what they could do is instead of teaching women or men, especially if these men choose the math track, even when they're not that good, just because they're competitive, maybe they are making the wrong choices. So we might want to teach them as well. But another way to do it might be to say, let's change the institution. Maybe the choice shouldn't depend on your competitive. Can I make the choice such that it doesn't depend on your competitiveness? Okay. So, for example, should we have a more gradual choice, like in the US, compared to a once and for all decision? Okay. Single-sex education, it comes up every time I talk, so here it is. You don't have to bring it up yourself. Who knows? So I think these are avenues for future research where, if you have any ideas, or obviously, I'm always happy to hear that people get excited about these things. Okay. That's it. Thank you.
I think we have time for maybe 1 or 2 questions.
There was one in the very back here.
Yeah, so in your laboratory task, I was really interested, it was fabulous talk, by the way.
Thank you.
In your laboratory task, I was interested in the role of stress. And the reason I'm interested in this is because in our lab, we've been testing acute stress. We just have people hold their hand in ice water for 3 minutes, and then we have them play risky decision-making games 20 minutes later. And we weren't looking for this initially, but we find dramatic sex differences. So the women become less risk-seeking under stress, and the men become more risk-seeking. And it changes their behavior in a number of ways. And so, in any sort of competition, you're gearing up for a race, or you're trying to do these math problems, your stress levels are going to go up. And so I'm wondering if you have any data or any hypotheses about how the stress in that context might be increasing those gender differences that you're seeing.
Yeah, so the question was on stress. So I have never measured stress. I'd be happy, I think it's an interesting question. By the way, just the first comment, how nice you like to talk, this is a very psychology comment. Economics talks, you would never ever hear this. So I still think it's a true comment, but anyway. It could be, I think it could be that it could be that a lot of it is driven by tolerance towards stress. Maybe we have to teach them to deal with stress. So maybe that is something that would be important. I think it's probably true, but I have no data on this.
Tolerance, I don't think it's that in our data, at least, because the men change too. So the men become more risk-seeking, and actually on the some tasks, it hurts them, and some it helps them. So it's not always a good thing to be risk-seeking. Sometimes it can be a bad thing, but they show it in both cases.
So what I can tell you is that risk aversion does not seem to be the driving factor for these gender differences in competitiveness. So that we have actually pretty good evidence on. And competitiveness may not always be very helpful either, right? Sometimes. There's a lot of evidence that women who are very competitive are seen as aggressive, and this is sometimes viewed very negatively. So there's maybe a good reason not to be that competitive in certain areas. If you cooperate with other people, that might be also very helpful. So we may have to be a bit careful about this. But I don't think it's I think if the channel is going to be risk aversion, I'm less hopeful, just because risk aversion doesn't seem to be that big of an explanatory variable in this gender difference in competitiveness.
I'm just wondering if you've thought about trying to design experiments to measure competitiveness as something that's multidimensional. It's like, say, the sports analogy that you were using. There are certain basketball teams where they talk about, these guys, each one is trying to make himself look good rather than thinking of the team. So right there, you have 2 different kinds of competitiveness.
So one way to think of that, so let me first say why we know so little about this. So literally the first paper in economics on gender difference and competitiveness was my paper with Urgnese and Aldo Rosicchini 10 years ago. In economics, we are very, very slow. Not like you guys, we publish very few papers a year. So we know surprisingly little about this. But thinking about the interplay between competing for myself or competing for others, even depending on who I compete against. So it turns out women are also often happy to compete against other women, much more than competing against men. So the big problem is competing against men. But this interplay between competition and cooperation is something that we have not touched on that much yet. So that, my answer is sorry, not yet. Hopefully in the future. But I think it's a great question, so really I think, ideally I hope that some people get excited about this environment and do something. I don't know yet. Yeah.
All right, so next we have Brian Knutson, and he's from Stanford University, the psychology department, and I don't remember what your talk is called.
That's okay. I'll say what it is. If I can find it. Let's see, it's here somewhere. Yes. Great. Right. So it's always a pleasure to be here, and it's an honor to be here with such esteemed colleagues. Contrary to what you might assume, I'm very grateful that I live so close to Berkeley. And it's always good to see old friends, too. I'm going to talk today about too much, and so I encourage you to stop me in the middle of the talk if anything I say is unclear, which will probably be a lot of it. And I'm going to talk about new things, so it's going to be rather unpolished, and I apologize for that. But if I didn't, then Kevin and my old colleagues who've heard this stuff before would fall asleep, so I've got to keep them entertained as well. So my goal in this talk is going to be to describe research that's occurred over the last 10 to 12 years in our laboratory. A lot of it's sort of what I would call basic research, where we're just trying to measure various things in the brain. But then to take those basic paradigms that we've developed and apply them across the lifespan. When I say across lifespan, I don't really mean below 20, but I mean above 60. So I'm going to try to describe differences that we see. So not only the basic findings that we see with these paradigms, but also differences that we see in older subjects. And why am I going to do that? Well, because the world is aging, and I don't just mean the globe. Of course, the globe is aging all the time, but I mean the population of the world. And so this is one of my favorite graphs that illustrates this. So this describes changes in the demographics of the population, I think, in the United States, but it could equally apply to the rest of the world. And this is an age pyramid. So in 1950, most of the people were young in the population. As we go to 2000, we're seeing that we're getting more middle-aged people, like myself. And then as we go into 2050, it's going to look more like a tower in Manhattan. So there are going to be fewer young people and more old people. And that's probably significant. That means that it behooves us to understand how older people think, feel, and decide. And we already have learned quite a bit from behavioral research about how aging changes thinking and feeling, although not so much about how aging changes decision-making. So to give you some examples of this is research on aging looking at intelligence, measures of intelligence. So aging, I'm sorry to say, decreases fluid intelligence. That means how many numbers you can hold in your head at once. So these are many different IQ standard measures of fluid intelligence. Here's age going from 20s to 80s. Here's Z-scores on these different tasks, which all correlate with each other, like speed of processing, working memory, long-term memory, and unfortunately the line is going down. However, all is not lost, because crystallized intelligence, measures of what you already know and can retain, seem to remain relatively stable into the 80s. So this is things like facts that you know about who was elected in the 2012 election and so forth. These hopefully will be retained. When we talk about affect, less was known about affect and emotion and how aging influences it. But for the last 20 years, people have been discovering quite a few interesting facts, including Muriel Niederle up there. She'll probably talk more about this. And it turns out there are systematic age changes in emotion as well. I think Kevin referred to this as well, such that as you age, even though your fluid intelligence is going down, so is your negative affect. So maybe you won't miss your memory so much. Another interesting finding is that positive, relative to negative affects, so negative emotions like irritation, anxiety, and so forth, positive affect seems to stay relatively constant, which leads to this so-called positivity effect, or you could say the non-negativity effect. And this is kind of an interesting observation, because when you think about how people make decisions, they're probably using some cognitive variables and some affective variables in ways that we don't understand. So contrary to the theory that everything declines, as with aging, we're finding out with behavioral research that no, some things decline and some things don't. And that potentially has significance for decision making. So the question that I'd like to try to just dip my toe in the pool of this vast question today is, does aging influence decision making? And we're really at an early stage in these kinds of studies, partially because the behavioral paradigms are not well developed for this sort of thing, and also partially because we know very little about the brain. So we're innovating as we investigate different methods for understanding what's happening in the brain as people are making decisions. But I also would like to try to touch on, if there are changes in decision making with aging, how does that happen? I mean, I don't mean just how psychologically, but how neurally is it happening? So these are the basic questions for the remaining minutes. How does aging influence incentive processing and risk-taking? So my lab has been looking at financial decision-making for a while, for like the last decade now. And for various reasons, it's a nice field to work in if you're doing neuroimaging, especially with fMRI, and I'll describe why in a few seconds. And also, can what we find about how aging might influence decision-making and how the brain is processing decisions help us to improve people's decisions, old and young? So I'll talk a little bit about some paradigms where we basically get people to expect financial gains and losses, and how that changes as people age. Then I'll talk about additional paradigms in which we actually get people to take financial risks, and talk a little bit about how that changes over the lifespan. And finally, I'll try to integrate what we found, which will be difficult, but I will throw out some very speculative ideas about what might be happening. And I think you'll see that it'll tie into some of the other talks that you heard this morning. So how do we even start thinking about incentive processing, how the brain anticipates good and bad? Well, one way is to look at what animals do, because animals tend to share a lot of the brain below the cortex with us humans. And I mean that anatomically and chemically and even behaviorally. And you can look at a number of things about animal brains. One of my favorite examples is you can stick an electrode at certain parts of a rat's brain and allow it to stimulate that electrode, and it will do so to the exclusion of all other activities. These areas that support this so-called self-stimulation can also be demonstrated, or this behavior can be demonstrated in monkeys and humans too. Most of these areas are below the cortex. They lie on the ascending trajectory of midbrain neurons projecting up to subcortical areas and cortical areas in the prefrontal cortex. And don't worry, this is very complex, but all I want to illustrate with this drawing is that you can also anatomically trace out these tracts in animals. And now with methods like diffusion tensor imaging, we can do it with humans. We can put you in a magnet and trace the integrity of these fiber tracts. And it turns out to look very similar to what I would see in rhesus macaque, for instance. And I will return to that later in the talk. But I'm going to talk mainly about functional neuroimaging, because new methods that we've developed allow us to look at activity in these deep brain regions. This is really an area that's deep in your brainstem that houses dopamine neurons, which projects up to subcortical areas and to prefrontal areas. A lot of these areas support this self-stimulation behavior in most species studies. The advance that really allowed us to start to ask these questions about what are these areas doing when people are anticipating good and bad happened in 1993 when functional magnetic resonance imaging was developed. And the advantage of functional magnetic resonance imaging was not only that it gave you good temporal resolution, that is a second-to-second temporal resolution of changes in oxygenation in the brain, but also good spatial resolution, not just on the order of millimeters, but such that you could go below the cortex. So you could use methods like EEG, electroencephalography, which has been around a long time, to get great temporal resolution, but you're going to have electrodes that are outside the skull. So you're not really going to know where those signals are coming from if they're emanating from deep in the brain. fMRI allows you to go down deep in the brain and look at localized changes in activity. There are other methods, by the way, that allow you to go deep, but they don't have the temporal resolution. So positron emission tomography, for instance, the best temporal resolution for that is 2 minutes. If you're thinking about decision making, decisions can happen very fast. But if I don't know, raise a certain decision scenario to you that you regularly engage in, you go to Amazon.com and you're looking for a book. And you're deciding whether you want to buy that, you look at the price, you look at the reviews. That's going to happen, that's going to evolve on the order of seconds. And that's the kind of temporal resolution, spatial resolution you can get with fMRI. And I am lucky because I'm going after both Emily and Kevin, and they've already described much of how fMRI works, so thank you guys. I'm going to describe just a task that's been a workhorse in our lab. There are many tasks like it. It's a task that we use to elicit activity in these deep brain circuits. It's called the monetary incentive delay task. It's based on tasks from the animal literature, but instead of using juice or other rewards, we use money. Why? Because humans tend to get very emotional about money. I mean, this is not widely known, I guess, before 15 years ago, but I guess most people on the street would have guessed that people get emotional about money. The interesting finding is that people get emotional before they even get the money, and that we can take advantage of with this task. So we can actually cue people with an uncertain cue that indicates they might make some money. They wait a couple of seconds in this task, then they see a rapidly presented target. They try to respond with a button press. Depending on the cue, and if they respond when the target's on the screen, they can either make money or avoid losing money. That's how the task works. So it's very simple. You can change the cue. So you can change the shape of the cue, indicating you can make money or lose money. Or you can also change other features of the cue, like how many lines are in the cue. That could indicate how much money is at stake, $0, 20 cents, $1, $5. So you can immediately start to manipulate all kinds of things, not just about outcomes, but also about expectations. And what we want to do is use fMRI to look in the brain when people are expecting gain and loss, and see if we can find parametric increases in activity in specific circuits using this method. So the innovation of this kind of paradigm is to try to separate the anticipation from the outcome and separately visualize what's happening in the brain. And so this is what's happening in the brain in this task. This is a statistical parametric map that Emily mentioned of 14 subjects overlaid on a representative subject's brain with cutaways here, 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 with a chunk taken out. You're looking inside the brain, excuse me. And what you see is in these subcortical circuits in the ventral striatum, I think they were mentioned before, to which dopamine projects. We're not looking at dopamine, but we know dopamine projects there. We see increased activity as people are anticipating making money. It's parametric or it's ordinal, so that the more money you think you're going to make, the more activity you see here. When they anticipate loss, you don't see the same ordinal increase in activity in this region. This is a time course of activity taken out of that region over time, just showing that what we can do is say, okay, we know the cue appeared about here, and we know that people responded here, and they got money here. So what happens when you anticipate making $0, 20 cents, $1, $5? Basically, you can show that before they respond and get the money, you see an ordinal increase in activity. So this is just a way of trying to map things in the brain, really. I mean, this might be related to excitement or positive arousal or expected value. It might be, and I'm going to argue that it is. But I would have to do additional experiments to demonstrate that. For instance, I would have to ask people, how did you feel when you saw that $5 cue? Right? And then I could correlate it with activity in that region when they saw the cue. So I could show that not only within individuals, but across individuals, activity in this region is not just correlating with how much money they think they can make, but some affective reaction they have to the possibility of making that money. And so that's what we did. We asked, basically this is old personality methodology, but you can ask people on all kinds of different adjectives, how do you feel when X happened? Or you can simply, there are other ways of just asking a couple questions, like how aroused and positive did you feel when you saw this cue? Okay. And the interesting thing about this space that you can derive from their affective ratings is it's two-dimensional. So it has two orthogonal dimensions of valence, going from good to bad, and arousal going from high to low. You rotate that through 45 degrees, you can get a positive arousal dimension and a negative arousal dimension. And the reason I'm focusing on that rotation is because we think not only does this reflect the operation of mechanisms in the brain, but also that it's evolutionarily adaptive. That is, the reason you have a feeling that translates into motivation is so that you can approach good things and avoid bad things, okay? So these are all a lot of teleological assumptions, but if we're right, that means that people, even for the same amount of money, if they vary in terms of how positively aroused they feel, how excited they feel, then we should see differences in their nucleus accumbens reaction to that cue. And that's what we see. We've seen it in a few experiments now. So this is asking people how excited they felt when they saw the $5 cue. And this is the percentage of signal change we see in that region in response to the $5 cue. Okay, so this again is more mapping, but it's important for us because we're actually interested in, well, this is a meta-analysis, in anticipatory affect, that is how people feel before they make a decision, because we think it can give us a way of predicting what people will do next. So just to go back to this meta-analysis, this is actually outdated now. It was done in 2008. So a lot of people have used this technique to elicit brain activation. And we can take those studies and just do a big meta-analysis of the results. And what you see is a pretty consistent pattern of activity, such that when people anticipate gains, you see more activation in these subcortical ventral striatal areas, including the nucleus accumbens. Interestingly, you see an opposite pattern for losses in parts of the insula, which we haven't totally nailed down, but we're going to use this to try to predict choice in a few seconds. In addition, you see differences for outcomes versus anticipation in this particular task. So you tend to actually see more prefrontal activity when people get gain outcomes. We can move that activity into the anticipatory interval by changing aspects of the cue, like the probability that you'll win. I won't go into that, but that's important because it's another component of expected value as defined in some economic theories. What all of these studies have done is allowed us to have a very crude model, a reverse inference model. And the caveat I want to give you right now is that we don't really know what we're doing. We don't know what activity in these brain regions means. That's part of the work of doing neuroscience, is that we have to figure out what the appropriate reverse inference is. That's why Emily was appropriately saying, well, it could be self-relevance, it could be value. We don't really know. We're still finding that out, and it's very exciting. But what we do know is that there are areas of the brain that, before you get anything, correlate with something about how much you value something. And that's exciting, not just from a psychology perspective, but I would advocate from an economic perspective as well. Because that suggests that you can then take that activation and predict something about choice. Okay? And from our perspective, if we're thinking about how people feel before a decision, what we want is markers of how excited they are, how positive and aroused they feel, and how negative and aroused they feel. Because the markers for positive arousal should allow us to predict they're going to go after something. And the markers for negative arousal should allow us to predict they're going to try to get away from that thing. Okay? So this is a very crude reverse inference, but it's kind of a back-of-the-napkin model we've been working with. One area that I'm not mentioning that we also have data on is the medial prefrontal cortex that you heard about earlier. And when we tend to see that activated is when people are integrating either within an option or across options, sort of different types of valuation, like is it good, is it bad, how likely is it, how far in the future is it, okay? So it looks like the medial prefrontal cortex is doing something more sophisticated that nonetheless has something to do with value. Okay, so that's the setup for studying older people. So now that we have these probes, what happens if we just look at some older folks that are healthy volunteers from the community, and we have them do these very simple tasks? Basically, one you can make a lot of hypotheses. One is that their brain is degrading, is degenerating, it is shrinking actually. Everything's going to pot. You're not going to see any preservation of anything. Everything's going to get worse. That's not what we see. Actually, what we see is that when they anticipate rewards, we see an equally robust response in their ventral striatum. They get equally excited about it. There's a correlation between excitement and ventral striatal activation. We do see, however, that when they anticipate losses, areas of the brain that are usually activated, like the anterior insula up here, are not activated as they are in younger adults. What we additionally see is that they just don't report getting as freaked out about losing money before they lose it as younger adults. It's not that they don't care. When they lose money, they don't like it. They have very negative ratings. But there's something happening during anticipation in the younger adults that's not happening in the older adults. And this is interesting because it might play into this idea that there is a positivity effect or an imbalance between positivity and negativity in older adults. Yes, Muriel. Yeah, we've controlled for wealth effects, and we don't find any associations, actually. Yeah, and we've done that in a number of studies. So this is a community sample, not a student sample, both for the young and the old. But that's a great question, because from an economic perspective, you might think, well, that increment in wealth just doesn't matter as much to them because they have a lot more wealth, which they do, by the way. But it turns out, interestingly, we may have reference-dependent effects or something like that wealth doesn't seem to really play into these differences that we see in the experiment, surprisingly, either affective or from a brain imaging perspective. So there's more work to be done there, but it's a very interesting, it's something that didn't pan out, actually. But it is interesting, I think. It's interesting from a motivational standpoint, because you might think, even if I have a lot of wealth, I still want to be motivated, or it's still adaptive to be motivated. So, maybe I'm going to do some scaling and set a reference point or something like that. There are a lot, I won't go too deep into that, but there are a lot of really interesting basic questions that we still need to resolve with this kind of data. Yeah. Let me go back, sorry.
Affects the loss anticipation for outcomes, no difference on either side? Or what was it?
Yeah, sorry, I didn't go into all the details, but the main finding with this task, I'm going to show you some other differences with risk-taking. The main finding that we find for this task is that older adults look like younger adults when they're anticipating gains. I mean, and that means they're both positive and aroused. When they're anticipating losses, we don't see as much of a signal in the anterior insula. And we also don't see them getting as anxious, but for outcomes, they look the same. There is no difference. Yeah, both sides, yeah, yeah. And by the way, I'm not going into the outcome response because I'm sort of focusing on anticipation because I want to get to choice. But there are interesting things that happen at the outcome that are slightly different than what I'm showing you, okay? That nonetheless fit the anatomy that I'll go into greater detail later. So why am I talking about this? I'm supposed to be talking about choice. Well, this gives us targets, right? So not just for studies that go into the brain, like Emily was talking about, but also for taking activity out of those targets and using it to predict choice, upcoming choice, both within and across individuals, okay? And so that's where we wanted to be, and that's what we've been doing for the last few years. Now, just as an aside, there's an interesting question of how are older people when it comes to financial risk-taking? Are they more risk-averse? I think a lot of people assume that. It's a stereotype that's out there that older people are just more risk-averse, okay? And indeed, in certain domains, they certainly are more risk-averse, like physical domains, as you can imagine, right? But if you take people into the laboratory and you subject them to a lot of different financial risk-taking tasks, you don't find a consistent answer with age, okay? So this is just a meta-analysis, not that I did, but Rui Mata did, looking at different risk-taking tasks. This is the Iowa gambling task. This is our task, the bias task, which I'll describe in a second. This is the balloon analog risk task. So these are just different risk-taking tasks. And what you find is the effect size of aging on risk-taking is very diverse. It's not different than zero, basically. And it's kind of task-dependent. And it looks like people, if the right thing to do in the task, the right thing meaning you make the most money, is to be risk-seeking, then older people are more risk-averse. But if the right thing is to be risk-averse, then they're more risk-seeking. Okay, so something is going on, but we don't know exactly what. Okay, so I'm going to describe to you findings that we have from a specific risk-taking task, which is sort of optimized for fMRI, but it's nonetheless more complicated than I liked. So this is called the Behavioral Investment Allocation Strategy or Bias Task. Now, I did this task, I constructed a task with Cami Coonan, who's now an assistant professor in Northwestern. She was a student in my class. She said, hey, can we look at investing in the magnet? And I said, that's an awesome idea. And she came up with this really interesting task that's meant to simulate aspects of investing. And it has some certain features which are interesting. So in this task, people play 20 blocks of 10 trials each. At the outset of the block, they know that they have 3 options to choose from. 2 are stocks and 1 is a bond. They also know one of those stocks is good and 1 stock is bad, probabilistically speaking. They know the probability distributions. They know that with the good stock, on average, they're going to make $10 50% of the time, but they're going to lose $10 25% of the time. And conversely, with the bad stock, they're going to lose $10 50% of the time and make $10 25% of the time. They can always choose the bond, and they'll make $1 if they do, okay? So, but they don't know which is which. That's the key to this task. So they have to kind of figure that out. And what we're trying to do is to get repeated measures on each subject so that we can get them to do everything. We can get them to take risks and not to take risks. We get a mixture of behaviors within each subject so that we can try to predict what they're going to do, basically. Subjects know this. They don't know which is which. So if you were in my magnet, you might see these 3, and then you might see the word choose. You'd have to choose one of those. Let's say you chose the left option, stock T. You would wait a couple of seconds, and you would see that because you chose stock T, you just made $10. And now you have a total of $20. But importantly, if you had chosen stock R, you would have made $0. Okay, so they're getting not only information about the stock, about what they chose, but about the market. What that allows us to do in this task is to calculate what would happen if that person had been a risk-neutral, Bayesian updating, rational by the standards of finance actor, okay? So we can look at not only when people are about to take a risk or avoid a risk, but we can also look at what's happening in the brain before they make a mistake. That is to say, they take a risk when the Bayesian actor is not, or they avoid risk when the Bayesian actor is taking the risk, okay? what do we want to do with this task? What we want to see is what's going on in their brain right here during anticipation. And does that help us to predict what they're about to choose? Okay. So, I mean, this was kind of crazy when we first started to do it. I mean, for various reasons I won't go into. We didn't think it would work, but it turns out it kind of worked. So that's why I'm telling you about it today. So we're going to look at what's happening in the brain before they take a risk or they avoid risk. And we're also going to look at whether they're conforming to or violating the optimal actor model or the rational actor model. And of course, we can now use our markers, right? So we can say, okay, we think, given a risk, what is a risk? A risk is an uncertain gain, or you wouldn't care. But it also involves uncertain losses, or it wouldn't be a risk, okay? So given that you're facing uncertain gains and losses, if you magnify the salience of the gains, what should you do? Take the risk, right? And if you magnify the salience of the losses, you should avoid the risk. Yeah, exactly. So that's the idea. So everything else being equal, and which we can hold equal in regressions, we can hold equal, for instance, what happened on the last trial, what the counterfactual was on the last trial, what the wealth level is, what the uncertainty level is, and so forth. We can say, if we take activation out of these areas and throw it into the logistic regression that's predicting you're going to take a risk or not, does that add to the prediction? And the answer is it does, and this is a horrible way of depicting a very complex regressions you saw before. But it's meant to just give you sort of a flavor of what we saw. Basically, we saw that before you're about to take a risk, you have increased ability of the nucleus accumbens activation to predict you're going to choose to take the risk, the stock versus bond. And this is especially the case if you're making a mistake. On the other hand, if you're about to avoid a risk, that's what this is, your insula is more activated before you avoid the risk, controlling for all this other stuff. And this is especially the case if you're making a mistake, okay? So without going into too much detail on these coefficients, there was a surprise in our data, and the surprise was that we got the best prediction out of these brain areas, out of the activity, when people were shifting strategies. That is to say, if I'm avoiding risk and suddenly I start taking a risk, that's when we get the best nucleus accumbens prediction. If I'm taking risks, suddenly I avoid taking risks, that's when we get the best anterior insula prediction. That was not something we predicted, it's something we've replicated in a number of studies since. So this looks very decision-y. It does not look like the random walk. It is not that the best predictor of what you're going to do is what you just did. Okay, this is very different from that. And I think that's significant, that's interesting, because it suggests there's some added value we can get out of these brain signals. What happens with older people? So now we've been able, the initial sample was PhD students at Stanford, not very representative. You might be curious to know how optimal their decisions were. They matched the rational actor model 75% of the time. I thought this was wonderful as a psychologist. My finance colleagues were horrified. These were finance students and religion PhDs too. There wasn't a significant difference between the two, but we probably need a larger sample size. When we go to a community sample of young and old, we see a big drop in optimal choices. So the optimal choices go down to 50%. So there's some difference there that I don't know what's accounting for it. But nonetheless, we can use the activity to predict what people will do. And the first thing we see right off the bat, if we just look at the behavior, the kinds of choices they're making, is that they make a lot more of a specific kind of a mistake, and that is they choose the wrong stock more often, so they make a risk-seeking mistake. This isn't exactly what I thought we would see, right? But that's what we see. And so we can start to think about this in terms of that model that I just laid out, right? A lot of things could be happening if you're just using those components. One thing is that they have more nucleus accumbens activity for some reason, which I'll get into in a few seconds. Another is they have less insula activity, so the brakes are off, right? And a third is actually that maybe, yes, there's something wrong with the nucleus accumbens, but the value integrator in the prefrontal cortex is not talking to the nucleus accumbens, right, okay? And basically, this is a spoiler alert, but that's what we think we're seeing. So if you look at what is causing these mistakes, if you look at the brain signals, you actually find a full mediation of the effect of age on this risk-seeking mistake by looking at the noise in the accumbens signal. So it's not that their accumbens isn't firing. It's not that the activity isn't up in their accumbens. It's not that it's not predicting they're going to take a risk. It's just flopping around in a random way. It's not directed always towards the right stock. This is actually a measure of noise which is time dependent, and I won't get into it, but Greg Salmonez-Larkin, who's responsible for the study, resurrected this marker from a 1956 von Neumann paper. But it's essentially a measure of temporal variability in the signal. And this has actually amazingly been replicated by other labs in Germany. So there's something noisy about that signal in the accumbens. Why? Well, I mentioned that there's a reward circuit, right? And we also know that dopamine coming up from below is not only important to the activity in this region, but also there are prefrontal connections coming down that control what's going on in that area as well. And so one hypothesis about what's going on is that there's nothing wrong with what's happening in the nucleus accumbens per se, but there's some input to the nucleus accumbens that is disrupted. This is where the neuroscience tools come in handy in a way that I'll describe in a second. So what we can do is, yes, please. Yes.
To what extent do you worry about, looking at these age differences,
Yeah.
to what extent do you worry about the time constraints of the task in the laboratory situation versus the lack of time constraints in the real world when people are making similar kinds of decisions?
Right. So there may be a lack of generalizability of these tasks because it's even worse than the magnet because we actually have to tightly control the time because the signal that we observe is collinear with the amount of time that people are spending. So essentially what we do with these tasks is we run them behaviorally. We find out the range of reaction times that people show on the tasks. We set up the timing so that they can respond on most trials accurately. So I'm not too worried about can they do it. But there's an additional concern about does this generalize to anything in the real world? I will show you some data at the end of the talk that suggests there is some generalizability to real world outcomes, but it's a real concern. And by the way, it's a concern for everything that we do in the lab. It's a concern for every study that measures risk preferences, uncertainty equivalence, and so forth. It's a concern for all that stuff. So I hope you'll keep asking that question. I don't think it's just time, by the way, either. So it's complex. It's a lot of things. So yeah, you have to. It's difficult. This is tough stuff. But you know, we have to try things and see if they work, basically. Yes.
Also for clarification, would you say in simple terms, what has changed with accumbens activity with age in relationship to whatever you're going to say, approach behavior, choosing to make the investment?
Absolutely, yeah. Just to reiterate that very back of the napkin model, we think in our lab, and not everybody agrees, that nucleus accumbens activity is a marker for a certain kind of feeling, positive arousal, that you feel when you're approaching something good, okay? And it promotes approach behavior, okay? So the implication is, the reverse inference, if you will, is if you just see a spike in that activity, somebody's about to approach something, okay? That's what we would predict. If you see a variability in that activity, and people are surveying different options, then we would predict that there's going to be more random approach behavior. They're going to take a risk, but it's going to be hard to predict which, if that makes any sense.
So in older people, the predictive value of that neural activity in terms of subsequent behavior is not as good?
Yeah, it predicts risk-taking, but it doesn't predict taking the right risk.
It doesn't say, okay, so
Yeah.
it still predicts you're going to approach.
Yeah.
But it no longer says you're going to approach the right thing.
Yeah, it seems less tethered to what's the optimal choice, if that makes sense. And I'll say more about that because we think there's a prefrontal input that's contributing to that, basically. So basically, what you're picking up on is a paradox. It's right here for us. I mean, we were like, what the heck does this mean? What we see in these gain anticipation tasks is maintained sort of excitement. We see maintained nucleus accumbens activity, so much to our surprise, by the way. But what we see in risk-taking tasks is some noise in that signal, okay? And parenthetically, what people also see in probabilistic learning tasks where people have to switch around between choices, the more complex they are, the worse older people are at those tasks, okay? So it's not that learning is exactly the same as anticipation. Learning probably involves a component of anticipation, but you have to be able to flexibly move that component around, okay? So one hypothesis is that there are age-related declines in updating the gain anticipation, right? And what does that mean in terms of our back-of-the-napkin model? Well, what it might mean is that the connection from the MPFC to the NAC is unreliable, okay? And that has functional implications, and by the way, it has structural implications too, One structural implication might be that if we could trace out the integrity, the fiber integrity of the bundles in that path, then we might see a specific decrement in that path in older people, and it might be related to worse reward learning, for instance. And that's actually what we see. So we're able to use a technique which is, I think, like magic. It's called diffusion tensor imaging, probabilistic diffusion tensor imaging. And this is not functional MRI. It's a form of MRI. But what it allows you to do is to see basically where water molecules are moving in the brain. And it turns out that most of the major fiber bundles have insulation, fat, around them. And so the more fat they have, the more regular that insulation is, the more water molecules will move along that fiber bundle. And so if you see a disruption in where the water molecules are moving, you can infer that something is different about that tract. Maybe it's degraded, maybe there's more crossing fibers, we don't really know. But we can at least get a measure of this tract integrity with this technique. Well, and moreover, what we can do is trace out this mesolimbic dopamine projections from the midbrain neurons to the nucleus accumbens, and then from there through the thalamus to the prefrontal cortex and back into the nucleus accumbens. Okay? Yes?
So these regressions line linear, or they turned out to be linear when you basically fit a flexible polynomial? Because throughout this talk,
Yeah.
the relationship with age that seems to be very linear, which is great. But
well, yeah, I'm showing you data too. So I mean, you might detect nonlinearity. Yeah. But the data is this data is not transformed. So a linear model fits these data, is what I would say. But I don't know if we've tested different specifications of linearity. So we started with the simplest assumption of linear model, but we could always update it too.
But it seems that here it's highly nonlinear, and you showed the regression previously, a regression.
Mm-hmm.
The last regression line that you showed.
This one.
Yeah, this one.
Yeah.
This doesn't look linear at all. And also, when you run a linear regression like this, it's very sensitive to outliers. Mm-hmm. So, for example, you see this guy that is 88 probably.
Yeah, this one. Yeah.
Yeah. If you take him out of the regression, it will flip the slope.
Well, it won't flip the slope, but it'll get better. I mean, what we have is robustness checks on the regression. So, you know, I mean, that's admittedly a fairly noisy, you know, association. But on the other hand, this is age. These are very different variables, right? These are the proportion of mistaken risk-seeking choices on this task, and this is age. So you could argue that that's not a very tight association. It turns out it's pretty highly significant. But these are very aggregated measures. This is behavior, by the way, too. This is not a brain measure. These that you're referring to, I think, are brain measures. So these are way tighter than I ever would have predicted. I have to say I'm kind of shocked by this data because I've dealt with structural data before, like volume, and volumetric measures do not have this kind of correlation with behavior. So we need to replicate. We're actually trying to replicate this now. But yeah, there's a question about, I mean, this is the first time we've seen this. So, you know, we probably have misspecified the model in some way. And probably not in a way that will fundamentally change the finding, but maybe in a way that we could fit the model better to the data. So yeah, but these are linear fits. But what I want to illustrate with these data points here is just the effect that we're seeing here. And that is that if you look at this circuit, this entire circuit, the fractional anisotropy or integrity of these connections, and you correlate it with reward learning, that is how fast you learn that one probabilistic cue is better than the other, and by the way, this is incentive compatible. One cue is giving you $1 66% of the time, the other cue is giving you $1 33% of the time in this task. I didn't go into the details, but you'll have to trust me that this is a widely used task. What you see is that aging is negatively correlated with performance in this task. What you also see is that aging is negatively correlated with integrity of this fiber bundle that projects from the MPFC down to the nucleus accumbens. Okay, this is a specific part of that circuit. That's not surprising because aging is negatively correlated with anisotropy in a lot of brain areas, although not all. What's interesting is that fractional anisotropy in this path is very positively correlated with performance on this reward learning task. And also that this fractional anisotropy completely accounts for the influence of age on learning in this task. It's a full mediation, and it's specific to this part of the circuit. So other parts of the circuit do not mediate this effect. So this is not a global brain effect. As far as we can tell, it's specific to this path. So this is, to me, really exciting. And I'll tell you why in 2 slides. But because one idea about this integrity is that it's a fixed quality, but another idea is that you could actually change it. And there's some evidence that it can be changed. Okay, so.
Can I just make a
Yes, yeah.
So the regression on the left-hand side,
This one.
you would think that it's, it's just decreasing in some constant rate through the lifespan, but I look at it and I'm saying, this is going off the cliff.
Yeah, you're right.
It's basically until your 60s, it's pretty stable.
That's not very good.
And then shift, boom, you are falling.
No, I think you're right. I think
highly non-linear.
Yeah, I mean,
it's not fluid intelligent. For example, it's something completely different.
I would feel better about like addressing your question if I could see the other distributions to see if a similar kink occurs, right?
So there is definitely a kink in the data.
On the other hand,
something wrong.
On the other hand, there are individual differences within age group, and so this variable, this integrity, overpowers age when it comes to predicting reward learning. That's what a full mediation would mean, okay? So we basically have a full mediation on whatever this measure is. We may need to fit it better, and I'm all for that. Actually, I'm glad you mentioned that because I haven't really played with the data that way. We're getting a bigger sample now too, of course. This isn't a huge sample.
Pushing on things that we talked a lot about inflection points. I think that this method of fitting linear regressions, you cannot identify inflection point. Inflection point is exactly this. It's a kink.
That's
something
true.
And here actually, I think that Bob should be very sensitive to this kink because of his research, not because of his age, of course. But here is the kink.
This is the fiscal cliff.
Yeah, this is the old age cliff. Here you see it, I think.
Well, yeah, we obviously need to do more work on the best specification, right? I totally agree. And keep in mind, these are physiological variables. So, I mean, these probabilistic algorithms have only been around 3 years, basically. So you could not see this 4 years ago. But I just want to say one more thing, which is if everything I've said is true, so if something is going wrong in the nucleus accumbens, the nucleus accumbens activity is related to some assessment of expected value. There's some problem with the input, that value integration, integrating expected value, if you will, and feeding it into the nucleus accumbens. How can we make older people do better on the bias task or the investment task? Well, one way is we just feed them the expected value information and see what happens. It's kind of boneheaded, but you can do that, right? So we actually did run people in different age groups on the bias task, and we did several different manipulations to try to understand what psychological variables might help older people to make more optimal choices. And what we found is that indeed, older people, again, this is a replication, make fewer rational choices than younger people in this bias task. But if you do various manipulations, so we thought that providing them integrated estimates of each stock option on expected value would improve their performance. Indeed, it does above this baseline for both younger and older subjects, okay? If we give them discrete values, that is a running total of what went up and what went down, they don't do as well. So this doesn't help as much. It's not as integrated, okay? If we totally interfere with their ability to hold anything online in working memory, that is, we have them do, at the same time they're doing this task, they're listening to tones, and they're counting how many tones were high versus low. It's very annoying. It has no influence on the optimality of their choices, okay? This suggests that whatever mechanism we're looking at is not a dorsolateral prefrontal, explicit sort of working memory buffer type mechanism. It's something more implicit that's lower in the brain. Interestingly, if you give them the integrated expected value information, they perform just like young people without the integrated expected value information. So that's good. I mean, that at least, this suggests that we know at least one way to bypass this problem. And the problem is, how many CEOs are going to give you that kind of information in their stock reports, right? But anyways, to summarize, what we're seeing in these very early studies is with age, we see a preservation in gain anticipation, actually, which I think is good news. But a reduction in performance on risk-taking and learning tasks. This may relate to a disconnection. This is our best guess right now, so it may change in a year. A disconnection between the MPFC and the nucleus accumbens. There are a lot of things we can do to try to test this more specifically. And it raises interesting questions like, can we reverse these changes either physiologically or circumvent them environmentally by providing different information and so forth. And I think, obviously, there are a lot of implications, at least for me as a psychologist. The basic implication for me is, can these findings illuminate how cognition and affect work together to inform choice, right? I mean, that's what we want to know. as psychologists. But there are other possible practical implications. For instance, can these findings facilitate optimal and targeted decision aids for older people if they need them? Can we promote plasticity in pathways that enhance the integration of value into choice, and how? I'm open to all ideas about this particular pathway, by the way. Can laboratory performance generalize to the real-world financial behavior? This is the question that was asked before. So we've started to look at real-life financial outcomes and try to correlate them, just as Muriel was, to performance on, like, the bias task, for instance. And what we find, interestingly, is that in an unselected, this is a community sample, the more rational choices you make on this task, the more assets you report having. And we can actually verify this with credit reports in subjects. So basically, the more you have in your bank account and the more you paid off on your house. So there do seem to be some relationships to performance on these laboratory tasks and real-world financial outcomes, which gives me some hope that there may be some generalizability. We have a lot to do, though. So can old dogs learn new tricks? We think so. And we think that understanding the psychology and the neuroscience of decision-making will help us to help these dogs learn their tricks. Thanks. And this is probably most important. Greg Samanez-Larkin dragged me into aging, kicking and screaming, and is responsible for a lot of these studies. And now I'm totally fascinated and seduced. So he really deserves a lot of the credit. I mentioned Camelia Kuhn in my lab and our funding agent. So thanks for your attention, too. Bob.
This is a kind of integrated. I was really interested in the little argument,
We can go back.
In the cliff argument you guys were having, and I wasn't. So, I may not get your point exactly right, but I think what you were saying is if you get to the age of 60, instead of that regression line just continuing in its little smooth trip, it's going to kink downward and drop. I got it right. Yeah, I've been around you enough now, so I think okay. So I don't want to argue about the math in this, but I was just thinking, Brian, that it might be interesting to hear you talk about those kinds of models in white matter tracks. So, for example, in some of the diseases of aging, like the dementing disorders, and Richard can sort of jump in here and tell me if he agrees, you see people who hang on for a long time, and they're sort of functioning okay, and then something happens, like they go into the hospital for an operation, or they have a bad cold or something like that, and then they kind of drop suddenly, and your forgetful relative becomes really totally dysfunctional. So what I was wondering is, how would you think about that kind of a phenomenon, that kind of nonlinearity, which might be part of late life, and how would you think about it in a very nicely described circuit like this that you're really modeling? So there's like a reserve, and then all of a sudden you drop below it, and then there's a sudden deterioration in the rationality of your decision.
So we're hesitant to depart too much from standard models because this is so novel. I mean, this is one of the first correlations with incentive decision-making and these kinds of measures in the literature. Let me show you some more data from the entire tract, from the entire pathway. So this is the VTA going to the NAC. Strangely and unexpectedly, in our case, there's a slight positive relationship with aging. I don't know how to explain that. But one thing I can tell you is that if you go from the nucleus accumbens then back to the thalamus, it's flat, okay? Then you go from the thalamus to the MPFC, and you start to see a decline, and you start to see this thing right here. So, and then you get to the tract that I was talking about, right? It's going from the MPFC down to the ventral striatum and then the nucleus accumbens. That looks more prominent. I mean, I think it's really interesting. No reviewer would allow me to do any kind of like sophisticated modeling on it yet, but if we get more data, which we're getting, we can actually try to verify whether there's a specific kink in these projections that go based. These are not, the difference between the ones that are going down like that and the ones that are not is the ones that are not are subcortical. The ones that are going down like that are running through the prefrontal cortex and they're glutamatergic. So that's interesting too. And these are the ones that tend to be associated with bad reward learning, essentially. And by the way, we've also correlated them with the mistakes in the bias task, and they seem to be correlated with that as well. Not as robustly, but they seem to be correlated. So I think it's an interesting observation. Like here, it's not as clear, right? This is going from the thalamus to the prefrontal cortex. It's not as clear. As we get more subjects, I think we'll be able to better estimate whether there's a nonlinearity in these associations. So I don't think it's inappropriate to start thinking about nonlinearities, but I don't.
My question to you is, if there were how would you talk about it in terms of this process?
I would. Well, it might be irresponsible, but
that was the idea. To get you to.
Have you ever heard of Phineas Gage? I mean, you know, one implication is that the steering wheel. Okay, let me be more figurative here. Let's say that this part is the gas pedal, and that's the steering wheel, right? Okay, so this part is saying go, it's good, right? And that part is talking to this part and saying, whoa, go over there, there's a tree over there, or something like that, right? Go that way, go that way. Now let's say take away the steering wheel and you just have a gas pedal. What would happen? Right, so it better have the right associations sort of burned into that circuit. I'm not saying that sounds very pessimistic. I mean, what I would leave you with is, well, what if we could strengthen those connections, right? So there is this emerging data to suggest that you can actually change the fractional anisotropy, whatever it's measuring, the integrity of those fiber tracts measured with DTI. So people have had rats run in wheels and stuff like that, and looked at motor to thalamic DTI connections and observed increases in fractional anisotropy after the rats ran on the wheel a lot. So I don't know what that means with respect to this particular pathway, but that's another way to think about it. I'm not assuming that this will go as an irreversible phenomenon.
So that would metaphorically be highly motivated, misguided behavior.
Yeah.
Yeah. No, that sort of makes some sense.
Which is like teenager. No, I don't know. I think it's erroneous to say older people are like teenagers, but Mara.
Yeah, so I had a question about because complex activities. You were saying
Yes.
It
I'll go back to the.
is a signal of positive arousal or arousal associated with anticipating positive rewards. And so I'm puzzled about this finding in the appendix of your Nature, the Semanis Larkin 2007, where it
40-page appendix.
Yeah. So where the nucleus accumbens activity also goes up for anticipating negative rewards.
Yeah. We have seen that the nucleus accumbens activity will increase during anticipation of losses. However, in almost all of our experiments, except for that one, there are some issues with that one, but the cues were literal in that one, basically. But we almost never see an ordinal increase. So we almost always see a bump that's sort of just like flat, basically. So do you want an image of this?
Sure.
Okay, so, and this is an old paper, but it's been replicated a lot. So here's a plot with data of peak activity. You know this one?
Yeah.
Yeah, okay. So to give you an example, so, and I'm sorry about so here's an accumbens VOI and various contrasts. This is gain versus non-gain, and this is high versus low gain. And these are the different conditions, right? And this is just peak activation. Before I show a time course, I'm just taking the peaks. So what you see here is that when you go from +0 to +20 to +1 to +5, it's popping up for +5, basically. It's ramping up. But when you go to -0 to -20 to -1 to -5, there's something kind of going on here, but it's not very ordinal. So that's what we often see. But I know what you're talking about in the Samanas Larkin, and I'm not sure why it's slightly different in that study. We have 3 categories. We have literal cues as opposed to just abstract cues. So we are trying to figure that out, actually. So, I mean, one idea behind the way that we're thinking of this is that first of all, people are always motivated, just to different levels. Second, they're always motivated in 2 ways, right? So positively and negatively. And it's kind of the relative level of motivations that will determine what they're going to do. So it could be that when they think they're going to lose, in this task at least, they can escape. Similarly, for gains, when they think they're going to get some money, they might not get it. So we would expect some level of activation. I don't know if that helps or not.
Yeah.
It's a rationalization, huh? This is so neuroscience-y. I apologize for that.
So in this picture
Yeah.
that we're speculating about in drop-off,
Yeah.
it seems like you could just as easily say, look, there's a person who goes way up, right? So the person who looks like they're about 90 and they go up. And
Yeah.
do you think it could be that it goes the other way? Like if you're still participating in studies when you're 88,
It could be.
then maybe you have, a really robust.
It could be that way. You have selection. I mean, we get healthy people that are community members. So they're selected from the community, but they are healthy, and some of them are pretty old. And so I don't know how representative that is of the world in general, right?
Yeah, no,
but
I wasn't asking really a
Yeah.
selection question. I was just sort of looking at the picture and saying,
It could.
if
you
we're
could
going to
interpret it.
speculate
Yeah,
about,
yeah.
it looks like, yes, clearly there's mutual information,
I mean,
right? And
yeah.
the nature of the correlation we can debate, but it'll be
I would
exciting
just-
to see once you've got a lot
I
more
would not
data
infer
points.
too much from this one
Sure.
study, but that there does seem to be some relationship. So that we need to collect more data to really understand the nature of that relationship and the generalizability, as you imply, right? I wouldn't place too much stock in outliers, basically, because again, like we just developed this method, right? We don't even know what exactly it's measuring, right? So this is very, very new stuff. So somebody could have moved their head, and usually we are very careful about our quality assurance on our data. Just ask any of my grad students. But I mean, that notwithstanding, we haven't had a lot of experience with DTI data. So maybe we don't know all the artifacts that can creep into that data. I am shocked actually by the tightness of the associations with behavior. I'm shocked. So this is kind of our newest, most wacky data. So yeah, sorry, you were going to ask something too.
The economists still are wondering, what do you have on the y-axis? So this 0.3 to 0.
Right.
Was there.
Let me bring it back up.
What is it exactly, and what's the scale? Is it a measure going between 0 to 1? So there is something
So you're
here.
talking about this y-axis?
Yes.
Right here? Yeah.
What is this exactly?
This is a relative measure of fractional anisotropy, which is, as I understand it, is a measure of along a tract. So you can basically, the cool thing about this method is you can actually, before people would just get measures of sort of all over the brain, where the water molecule is moving, and sort of how coherent is that movement, right? But the problem with that method is that, stop me if this gets too geeky, but the problem with that method is that if you have crossing fibers, then things are just a mess there. And there may be tracts going through there, but you're going to lose it. You're going to lose the tract. So what you can do with this kind of method of diffusion tensor imaging, probabilistic tractography, is you can say, I know from monkey studies that there's a tract, and it's running from the VTA, or the midbrain, to the nucleus accumbens. I'm going to seed this, I'm going to seed that. Find all the fibers that are going from here to there, right? So using like, vector type algorithms, find those fibers, and then narrow it down to the 200 most coherent fibers, okay? Once you've done that, then you can say, okay, along that pathway, tell me what's the coherence of the water movement. That's what this is supposed to be. And that's what this measure is. Normalized for sort of the whole brain measures of water movement. And so that's what these tracts are. Actually, there's a lot of crossing fibers here, but we've seeded here and seeded here. It's identified the tracts. Then it takes this measure of fractional anisotropy, okay? And that's against the backdrop of fractional anisotropy all over the brain. So it's a relative measure. Now, if I say anything more, I'll just be making stuff up, because physicists have figured this out. But the advantage is that you can separately identify the tracts and then estimate this fractional anisotropy along those tracts. And that's how we can pull out these subcortical tracts. If that makes any sense.
Yeah. I wanted to follow up. Is it something cardinal or something ordinal? So, for example, if I'm 0.
It's not cardinal. It's not cardinal.
Okay.
Can you stand closer to the microphone?
Oh, yeah, sorry. Yeah, sorry. I was getting engaged.
Okay.
Yeah, it's definitely not cardinal, but neither is like the fMRI stuff, not cardinal. Definitely ordinal.
We have time for one more question.
Okay.
I have another one.
Yeah.
But I was going to ask, since what Brian's really talking about now is sort of the development of the highways that connect the different parts of the brain. And he's talking about how in late life, those highways get some potholes on them. Thank you.
I can use that analogy.
Yeah, welcome to. And I thought maybe it'd be useful if you could also tell us just a little bit about the development of tracks in the adolescent brain, and
right.
and what we know about that, and how that. So now he's not talking about areas that are coming online, but he's talking about the connections between areas. It's a different way of looking at the brain. So.
Right. I mean, we think obviously that we're going to, one day we'll have imaging that's integrated, right? So we'll be able to say, I see this functional change, I'm linking it to the integrity of that path, et cetera, right? And that's where we'd like to move. Of course, in the adolescent brain, it is true that these fiber tracts are laid down at different stages of development. And I'm not an expert on this. Jay Geed and Paul Thompson at UCLA are really great at this kind of stuff and have massive databases on this. I don't think they've done as much of this probabilistic tractography, by the way. They've mostly focused on just general tracts that are easy to trace in the brain. So I still think there's a growth industry here looking at subcortical tracts over development. So I actually don't know, I should know this, but I don't know how much has been done with these subcortical tracts and looking at development over adolescence. But the lore would have it that the subcortical tracts develop first, and this is kind of old from animal literature, right? The Canard principle. The subcortical tracts develop first, and then it's the prefrontal ones that sort of come online later. I wish I could tell you a study that shows that in humans longitudinally, but I don't. That's not to say there isn't any, but if there wasn't any, I wouldn't be surprised.
Has anybody looked in adolescence at the integrity of, let's say, subcortical to prefrontal tracts as an individual difference measure that would predict dumbass behavior?
No, not that I know of. If anybody would have done it, that would have been B.J. Casey. Maybe Kevin knows.
Yeah, she has only one or two papers, and it's not dumbass behavior per se, it's performance on one of her affective go-no-go tasks. And I forget what the exact result is, but they seem to have stopped using these kind of FA measures. I know they went through a period where they tried them out a lot.
It sounds like a really smart approach, that would tell you a lot more about the developing or integrity of the adolescent brain, and also in late life, the sort of the degenerating brain.
But I mean, we're collecting all those measures in our work. We just haven't integrated them.
I mean, one thing I have to stress, and this is true with both fMRI, just so everyone is on the same page, and DTI, is that we don't know what we're doing. Like, we have these new measures, they've been around for 10 years. We still are not getting the most out of our data. Most fMRI studies have all kinds of temporal resolution that people aren't taking advantage of because they're using old statistical models and designs, right? So every year, I mean, you guys who are doing fMRI can vouch for this. You go to HBM, your human brain mapping, and you see 3 new techniques, you're like, oh my God, I got to try that out, right? I mean, so this is even more so with DTI. And part of finding this stuff involves knowing where to look. So I knew I wanted this pathway because I knew Suzanne Haber had done the track tracing studies in rhesus macaques, and that the tracks went there. And so I was down the hall from a guy named Brian Wandel, who's been doing DTI for like 8 years, right? On the visual cortex. He just never bothered to go to the front of the brain, right? He didn't think to go up there. He was looking at dyslexia. He was like, yeah, sure, here, you can use my stuff. So this kind of exchange is magnificent, I think, for seeding that kind of development, not just of theory, but of methods.